In this video, I wanted to go over a couple questions, just four of them, about moment arms that were on the exam that some people struggled with. So and maybe before we jump into this, let's just remember what a moment arm is. Very roughly speaking, you can think about it as the perpendicular distance from whatever force is acting on something to the joint that we care about. Generally, we can think about this in two ways. We can think about it as weight force moment arms, where you have some weight and gravity's pulling it down, and so your moment arm is going to be the perpendicular distance going off like this. It'll always be parallel. Or you can think about this as muscle moment arms. And the way to think about that, that's roughly correct, is it's the shortest distance from the muscle's path to the joint center. And this first question will get into that very nicely. But moment arms are useful to know because we have this relationship that the torque produced by a certain force is equal to whatever the force is times that moment arm. So if a moment arm is big, a small force can produce a large torque. And likewise, if a moment arm is small, even a very large force won't produce very much torque. And that's what this first question is getting at. It's asking about the peroneus brevis muscle. This is on the lateral side of the ankle. Goes up like this. This muscle is an important everter of the ankle joint, but we're not talking about eversion here. We're talking about, I probably should have said the dorsiflexion, plantar flexion degree of freedom about the ankle joint here. So maybe it's not obvious in the way the question is written, but we're specifically talking about dorsiflexion, plantar flexion. Peroneus brevis here, and this happens to be the case, it has a moment arm that is very close to zero. So what does that mean? Let's write out torque equals force times moment arm. So does that necessarily mean the muscle is very weak? Well, no, not really. Because the muscle could be super, super, super strong, but if the muscle path passes very close to the joint center, even that very large force would get multiplied by something very small. So that doesn't make sense. And likewise, for both strong and weak muscles, these arguments don't really make sense because the moment arm of a muscle actually has nothing to do with its force production capabilities. We actually saw that in the question in the last video about the gluteus medius versus the gluteus maximus. The thing that determines the strength of a muscle is its PCSA. The thing that determines how much torque a muscle produces at a specific joint is the moment arm of that muscle about the joint. Okay, how about this one? Even very small forces from this muscle will result in a very small or large. Clearly there was a typo there, so I should definitely adjust this one. Not sure about that because the typo makes it unclear. Even very large forces from this muscle will result in a very small ankle joint torque. Well, that actually seems correct because if the moment arm is very close to zero, let's say we had to produce a force of 1,000 pounds, and the moment arm, we're going to multiply that 1,000 pounds by 0.000001, some number really close to zero. Well, that's going to give us a really small amount of torque, right? So despite my typo in this previous question, this does seem to be the best answer, although I may have to adjust it given the confusion that might have resulted from this. Okay, how about this question? The triceps, which are these, hopefully you know that, pictured along with the biceps in this figure, are made up of three muscles, hence the name, and they create an extension torque about the elbow joint. So those muscles make the elbow go like this. If you want to know the maximum elbow extension torque that the triceps can generate in an isometric contraction, how would you do this? So we just talked about the torque production for one force, which is going to be the force times its moment arm. And then when you have multiple forces, and this is something I want to go into detail in this unit, is thinking about when you have multiple forces contributing to the torque at a joint. All you need to do, and this is something that is on problem set 3, which is due on Thursday, all you need to do is you just add up the individual torque. So say the first tricep muscle has some force and some moment arm that creates some torque, and then you add that, maybe we call that F1, moment arm 1. Then you can just add up the second force and the second moment arm, and add up the third force and the third moment arm. So we're going to be searching for an answer to this question that is hopefully describing this process. Multiply the PCSA by the specific tension of muscle, and then add up the result. Well, okay, what does that give us? The PCSA by the specific tension. PCSA times this. This is why having that sheet that has this on us would have been useful for you on the exam. This would have given you the maximum isometric force, which is good, because that's the maximum isometric force the muscle can produce. And if we multiply that by the moment arm, it would give us the maximum torque that each of the muscles could produce. So this seems like a reasonable answer, despite the maybe 3 layers of complexity here. Multiply the maximum isometric force by the, I'm already sensing the problem here. This is also the same thing. Okay, so this is also a reasonable thing to do. Multiply the maximum isometric force of each muscle by the moment arm of each muscle, and then add up the result. Oh, what did we miss here? Maybe this is why you had such a hard time with this question. What did we miss here? Doing this would just add up the forces. It wouldn't take the moment arm into account. So I guess that one's not a very good answer. Multiply the physiological cross-sectional area by its optimal fiber length. Well, that would not really give us anything reasonable. And it certainly wouldn't give us the moment arm. So I don't think this one is correct. Multiply the maximum isometric force by its optimal fiber length. Again, also, I don't think that's a reasonable thing to do because it doesn't really tell you anything meaningful. So I do think this is the best answer, although clearly, given that even I was a little confused by this, this is maybe a few too many layers of complexity for a multiple choice question on a timed exam. This one, happily, is more straightforward. This is going to be asking about a weight force moment arm. So let me just sketch out what the weight force vector for this kettlebell would be. In this position, how large is the moment arm of the kettlebell weight force about the shoulder joint? So that's this one. Here's the shoulder joint. Now, of course, you don't know what it is, but you can eyeball it, and it looks like it's relatively small, correct? So I'm going to be looking for an answer that's relatively small. A few inches, that seems reasonable. 2 or 3 feet, I don't think so. This one I put in here because 2 or 3 feet might be the length of your arm, but it's not this length that's the moment arm, remember. It's the perpendicular distance. So if we draw a schematic off to the side here, and here's the arm coming down and the shoulder joint is right here, we want, from the direction this force is going in, we want the perpendicular distance. So we don't want this distance, which is several feet. We want this distance. Notice how this is perpendicular here, parallel to the ground, because the weight force is vertical. So I don't think this one makes much sense. I certainly don't think 6 or 8 makes sense. And then maybe this is a little bit of a tricky one here. The moment arm is exactly 0. I think you could make a reasonable case for this, although from what I recall, not too many people actually put this as an answer. Nevertheless, I think if you do, now you could think about, could this moment arm be perfectly 0? I think it could, but what you'd have to do is you'd have to get the kettlebell like perfectly above your shoulder joint. So the force is going like this, and then the line of action goes straight through the shoulder joint. So maybe note here to adjust this one, although I do think this is probably the best answer, even though this one is maybe reasonable. Okay, last question. A recent study of elite distance runner, this is true, this is from a study I read recently, concluded that having a smaller Achilles tendon moment arm was associated with better running economy, which means better performance. Why is this unexpected? So why, it seems strange, right? You would think that if your Achilles tendon moment arm is really big, then your calf muscles could produce a lot of torque to propel you forward. So that's pretty much what this says. You would expect that what the response is here. Let's go through them. You would expect that a small moment arm would decrease ankle torque produced by the calf muscles. Yeah, it probably would, because if you produce some amount of force F and you multiply it by some small moment arm, you would think that would give you some small amount of torque, because torque equals force times the moment arm. So I like this answer. You'd expect a smaller moment arm would decrease the maximum isometric force of the calf muscles. Well, no, because remember, moment arm is totally independent of the force production capabilities of a muscle. Given a moment arm only, you can't really say anything about what the force production of a muscle is, only what the torque produced by given force is. How about this one? You would expect a smaller moment arm would decrease the maximum shortening velocity. Well, again, doesn't really say, and it doesn't really, the moment arm alone doesn't really tell you much about the shortening velocity of the muscles. That's actually something that's a property of the muscle, not its distance from the joint. Lastly, you would expect a smaller moment arm would result in a narrower width of the force length curve. Again, the moment arm doesn't really tell us anything about force length or force velocity or maximum isometric force. It only tells us about torque production. So for this one, I think this is probably the best answer. So that was analysis of the questions that more than about half of people had difficulties on. And as we noticed, we found a few issues or points of contention that I think are reasonable. So I will be curving this exam by several points. But hopefully you found this useful, and hopefully weren't too troubled by the initial results on the exam.